In this video, we are going to do 3 examples finding the radius of convergence for power series. So let's take a look at this first example. We would like to find the radius of convergence. In fact, we'll give the entire interval of convergence for the power series whose terms look like x to the n divided by the quantity 4n minus 1. Let me rewrite this first example just one time so that we can really identify the coefficients and the center, just for practice. So we can say that this is going to be the series summing from n equals 0 to infinity, terms of the form 1 over 4n minus 1 times x to the n. And if I want to really highlight that the center is 0, I could write this as x minus 0 to the n. Okay, so this is a bit of a silly thing to write. I'm just going to do that for this first example so that we can point out that for each value of the index n, the coefficient for that term in the power series expansion is 1 over 4n minus 1. And then this tells me that the center is at 0, which is often the case with power series. Okay, so this is our power series. Now, as we discussed in the previous video, we are going to determine the radius of convergence for this power series using the ratio test. So what I would like to do is set up the ratio test expression. So we'll say the limit as n goes to infinity of the absolute value of this expression, but for the n plus 1th term. So kind of going back to how I originally had it, let me write x to the n plus 1 divided by 4 times n plus 1 minus 1. Okay, so this is our series term for the index n plus 1. Then I'm going to divide that by the nth term, but that's like multiplying by the reciprocal. So I'm going to multiply this by 4n minus 1 divided by x to the n. Okay. Let's now collect like terms. And for the ratio test, you're almost always looking for things to cancel. So I'm going to situate this xn plus 1 over this x to the n, and then I'll pair up kind of this 4n minus 1 expressions so that we can say that this is the limit as n goes to infinity of x to the n plus 1 divided by x to the n times 4n minus 1 over 4n plus 4 minus 1. So overall, that's 4n plus 3. X to the n plus 1 divided by x to the n is going to leave us with just one copy of x in the numerator. So this x to the n will divide into that. And then this is a rational expression in terms of n. The numerator and denominator have the same highest power. So this goes to the ratio of those leading coefficients, 4 over 4. So basically, this expression goes to 1, which means that the limit of this expression as n goes to infinity is going to be the absolute value of x. Okay, what the ratio test tells us is that if this limit is less than 1, then the series would be absolutely convergent and therefore convergent. So if the absolute value of x is less than 1, this converges. If the absolute value of x equals 1, it's inconclusive. Kind of set that aside for a second. If the absolute value of x is greater than 1, so the result of this limit computation is greater than 1, then it diverges. So what we can say right now is that we converge, or the series converges, if the absolute value of x is less than 1, and diverges if the absolute value of x is greater than 1. We need to check, in order to provide the entire interval of convergence, what happens right when the absolute value of x equals 1. So that means that we will test manually the series that we would get if we plugged in either x equals 1 or x equals negative 1. Let's go ahead and do that now. I think I'll do that down here. So check about the left side first. So what happens if x is negative 1? If I plug negative 1 into the series, it's going to take the form of the infinite series from n equals 0 to infinity, negative 1 to the n, divided by 4n minus 1. This is a series of numbers. We spend a lot of time evaluating when a series of numbers converges or doesn't converge. And I don't want to go through the whole test. What I would like for you to do is look at this and recognize what applies. And you can work out on your own to the side the test in question here. So this is an alternating series. We have this -1 to the n. It's an alternating series, which means it's actually pretty easy for it to converge. We just need the expression 1 over 4n minus 1 to go to 0 as n goes to infinity. That happens. And also to decrease. That's not too hard to show that that also happens. So the check I just did out loud is the alternating series test. So this converges by the alternating series test. Okay, so at least one of the values satisfying that the absolute value of x is 1 actually gave convergence. Let's check the other one. What happens when x equals 1? Go ahead and see what happens if I plug 1 in for x, and then I will finish the problem. Okay, what's going to happen when x equals 1 is that x to the n term is just going to turn into 1. So our series becomes the infinite series, indexing from 0 to infinity, 1 over 4n minus 1. Again, I don't want to write out the full argument here, but you should definitely be able to support the conclusion that I'm about to make. And that is that this diverges. So looking at this expression, we see this n in the denominator and no other terms with the index n, which makes us think that this expression produces a series which probably behaves like the series whose terms look like 1 over n. That's the divergent harmonic series. I would take this expression and compare it to 1 over n with the limit comparison test. So this diverges by the limit comparison test, where we're comparing it with the divergent harmonic series. These terms look like 1 over n. Okay, so we manually checked the two values of x that give us an inconclusive result after the ratio test. So x equals -1 gave us convergence, x equals 1 gave us divergence. So that means we can now say that the interval of convergence the domain on which this power series converges is going to be including -1 up to but not including 1. So that's going to be square bracket -1 through 1 parentheses to indicate that -1 is included but 1 is not. This is the interval of convergence, but what we're actually focusing on in this lecture is the radius of convergence. That comes from this inequality right here. So our power series was centered at 0, and then we're saying if x is any number within distance 1 of 0, we get convergence. That's the radius. So from this, really comes right out of the result of the ratio test, we can say immediately with no endpoint analysis necessary what the radius of convergence is. So the radius is 1. So the radius of convergence is 1. What this means is that if we just want to know the radius of convergence, we set up the ratio test and we get to the radius. Okay, so if I just ask you for the radius of convergence, I'm just looking for this number. If I want to give the interval of convergence, that's when we need to test the two endpoints in addition to finding the radius. In this second example, we are looking at the power series whose terms look like -1 to the n times x to the n over the quantity 3 to the n times the natural log of n. If you're wondering why this series is indexed from n equals 2 to infinity, notice that the natural log of n in the denominator would give us an expression that was not defined when n equals 0 or 1. So those first couple terms are chopped off, but that doesn't affect the radius of convergence. So to find the radius of convergence for this power series, let's set up and evaluate the ratio test. So we'll say, what's the limit as n goes to infinity of the absolute value of this expression with the index being replaced with n plus 1. So I will write -1 to the n plus 1, x to the n plus 1, divided by 3 to the n plus 1 times the natural log of n plus 1. We need to divide this expression by the nth term, or the terms here with the index just set at n. That's like multiplied by the reciprocal. So we'll have 3 to the n natural log of n divided by negative 1 to the n x to the n. Okay. As usual, things are going to pair up here. The first observation I want to make is that whenever you have these negative ones, like negative 1 to the n plus 1, or negative 1 to the n, or negative n to the n minus 1, they don't matter in this expression, in this computation, because we're taking absolute values. So I can basically get rid of these negative 1 terms. Then let's see, x to the n will divide into x to the n plus 1, leaving us with just one copy of x. So this will divide into the numerator and leave us just with an x in the numerator. Similarly, the 3 to the n in the second numerator will divide into the first denominator, if you will, leaving us with 1/3, a term that looks like 1/3. And then the natural logs, I'll leave them as they are, and I'll finish evaluating this limit, and then I'll explain how to figure out what natural log of n over natural log of n plus 1 does as n goes to infinity, kind of as an aside. Okay, so after all this cancellation, what are we left with? We have the limit as n goes to infinity of x over 3 times the natural log of n divided by the natural log of n plus 1. The limit of the expression natural log of n divided by natural log of n plus 1 goes to 1 as n goes to infinity. I'll work that out in just a second, but I want to focus on the main computation first. Therefore, the limit of the absolute value of x over 3 times these natural logs, natural log of n divided by natural log of n plus 1, goes to the absolute value of x over 3 as n goes to infinity. Okay, so absolute value of x over 3 is the result of the ratio test. In order to have convergence, we want this to be less than 1. If it equaled 1, that's the inconclusive case that you would test the endpoints for. If it's greater than 1, we have divergence. So the radius of convergence for this power series is determined by taking this result and setting it less than 1. This tells us that the absolute value of x needs to be less than 3. In other words, our power series converges for all x values between -3 and 3. This power series is centered at the origin. So, we have 3 units to the left, 3 units to the right. This tells us that the radius of convergence for this power series is 3. Okay, so that is the radius of convergence for this particular power series. Let me now, just as an extra, compute this limit, just in case you weren't sure where this came from. I'm going to switch from natural log of n to natural log of x, and likewise for the denominator, natural log of x plus 1, because n here is an index, and I'm going to end up using L'Hopital's rule. And if I'm going to take a derivative, I'd like to think that I'm working with a function of all, say, x values greater than 1. So how about we say the limit as x goes to infinity of natural log of x divided by the natural log of x plus 1. It's an indeterminate form because this goes to infinity, this goes to infinity. So with L'Hopital's rule, we get that this limit is equivalent to the limit as x goes to infinity of 1 over x divided by 1 over x plus 1. You can multiply the top and bottom of this expression by x plus 1 over x plus 1, like that. So that overall, this is going to be the limit as x goes to infinity of x plus 1 over x. And then that limit is indeed 1. Okay, so that's where this computation came from. All right, so that wraps up this problem. We found the radius of convergence to be 3. I'm not going to check the endpoints for you, but I will reveal the answer in just a minute. So if you'd like to pause and work out what happens when x equals -3 and when x equals 3 to determine what the interval of convergence is, go ahead and do that now, and then I'll write down the answer. Okay, I thought I wasn't going to work this out, but let me just fill in some of the details for the endpoint analysis. When x is -3, what you may have gotten was that your series turned into a series of positive terms. So indexing from 2 to infinity, 1 over the natural log of n. This series diverges. You can show that by the ordinary comparison test with the harmonic series. 1 over the natural log of n is greater than 1 over n for all n greater than or equal to 2 for our series. So this diverges. And again, you can just do a regular ordinary comparison test with a harmonic. On the other hand, when x equals 3, I believe it's going to be an alternating series that does converge. You get n equals 2 to infinity. Yes, the 3 to the n's cancel out, and you're left with -1 to the n over natural log of n. That satisfies the hypotheses of the alternating series test. Okay, so the radius of convergence we already worked out without any endpoint analysis, and then just by checking the two values x equals -3 and x equals 3 manually, we can say that the interval of convergence does not include -3, but does include +3. Okay, so that's our radius of convergence and our interval of convergence. Let's do one more example. Okay, for our third and final example, consider the power series whose terms look like n factorial times the quantity 5x minus 1 to the n. This is not necessarily presented in the traditional power series notation, so the first thing I'm going to do is actually rewrite this so that it's clear what the coefficients and center for this power series are. But actually, we can work with this the way it is to find the radius of convergence. So after doing the conversion to a more traditional looking power series, I'll actually revert back to this for the ratio test. So first, let me just say that this is going to be the series from n equals 1 to infinity of n factorial. Then what I'm going to do is factor a 5 out of 5x minus 1. So I'll write that as 5 times x minus 1/5. So that this, if I distribute the 5 back, turns into 5x minus 1, and then all of that raised to the nth power. Okay. Now, 5 times something raised to the n is the same thing as 5 to the n times this quantity to the n. So I can write this as the infinite series, index from 1 to infinity, of n factorial 5 to the n times x minus 1/5 all to the nth. Okay. Written this way, we can see that the coefficients for this power series look like n factorial times 5 to the n for each index n. So these are the coefficients, and then 1/5 is the center. Nothing I just did is necessary to find the radius of convergence. I just wanted to do a little exercise in rewriting the series expression. So let's now do the ratio. Let's now do the ratio test in order to find what the radius of convergence for this power series is. So I'm going to work with the original expression. It works just fine. So we'll take the limit as n goes to infinity of the n plus 1 version of this expression. So that's going to be n plus 1 factorial times 5x minus 1 to the n plus 1 all over the expression as it is in terms of n. So that's n factorial times 5x minus 1 to the n. In the usual way, when we see a factorial inside of a ratio test, we want to simplify that. And here what we can do is think of n plus 1 factorial as n plus 1 times n factorial. So we've seen this a couple of times now with the ratio test. So that will let us simplify those factorial expressions, and then these will simplify nicely so that this becomes the limit as n goes to infinity of the n factorials cancel, leaving me with just this n plus 1 term. And then here, for the second expression, 5x minus 1 to the n will cancel out that leading term in our exponent in the numerator, so that this reduces to just 5x minus 1 to the 1. So 5x minus 1. Here's how we're going to analyze this limit. We have an n and an x, but be careful, these represent different concepts. N is the index which is going to infinity. So this leading term here, n plus 1, is growing arbitrarily large. X here is unspecified, but the idea is that we're testing any possible value of x. When you see this x in this limit here, you need to imagine that it's a fixed number. So x is something fixed, n is what's going to infinity. So what happens to this product if x is fixed and n is growing arbitrarily large? Well, there are actually two situations. If x is actually 1/5, so if I plug in the center value, then 5x minus 1 is 0. So this product here, n plus 1 times 5x minus 1, turns into n plus 1 times 0. That's just 0. In that situation, we would be saying, what's the limit as n goes to infinity of the number 0? It's 0. Let me go ahead and write that down. On the other hand, if x is any other value away from the center, so if x is not 1/5, no matter what it is, it's fixed. So 5x minus 1 is a fixed number being multiplied by n plus 1 as n goes to infinity. So if this is not 0, this product is going to go to infinity. According to the ratio test, that tells us that our power series converges when x is 1/5, as it should, because every power series converges at its center, and diverges otherwise. So this is a situation where our power series only converges at one value of x, only at the center. We describe that using a radius of convergence of 0. So this is the situation where a power series only converges at its center. That's like having a radius of 0. The interval of convergence isn't really a proper interval, it's just a single point. So if you wanted to describe it, you could say that this power series only converges at the single element 1/5, so just at one value of x. Okay, that wraps up our third example. So in examples 1 and 2, we had radii of 1 and 3 respectively, and here we have a radius of 0. I'm just realizing now that I would like to add one more example. So there's actually going to be a fourth example in this video where we will have a radius which is infinity. So let me just tack on one more example so that we can see what the ratio test would give us if our radius was not 0 nor a finite positive number, but actually if we wanted to conclude that the power series converged for all possible values of x. Okay, so for our new fourth example, let's consider the power series whose terms look like x to the n divided by n to the n. I'm going to do the ratio test on this expression, and it's a little bit of an advanced limit, so I'm going to do it two different ways. I hope you like at least one of them. So let me set up the limit as n goes to infinity of the quantity x to the n plus 1 divided by n plus 1 to the n plus 1, and then times the reciprocal of the expression as it's given to us, so n to the n divided by x to the n. Okay, in the usual way, let's pair up like terms, but I'm going to do something a little different here because I have these two terms which look like they should go together, but notice they have different bases and different exponents as well. So I'm going to do a little bit of maneuvering there. The x terms pair up right away, so we can say that this is the limit as n goes to infinity of x to the n divides into that, leaving us with just x. Then what I'm going to do is take the denominator that I started with, and I'm going to write it just like it is. So that's n plus 1 to the n plus 1. But then what I'm going to do is make this expression, which doesn't match either piece, different base, different exponent, I'm going to make it match the exponent. So that's going to be n to the n plus 1 But now I've done something a little unfair. I've changed my expression. So let me also divide by 1 copy of n. That should take care of it. Okay. So overall, this is still n to the n, but I've written it in such a way that I can now rewrite the second term so that it's going to be n divided by n plus 1 all to the n plus 1. Okay, this is positive, this is positive, this is just plain old x. So as I write this one more time, let me take care of this absolute value. This is going to be the limit as n goes to infinity of the absolute value of x times this number here will be n over n plus 1 to the n plus 1. And then I'm going to have times 1 over n. Just like we had in our second example, part of this limit needs a little bit more work. Let me go ahead and tell you what the limit of this middle expression is as n goes to infinity, and then I will give you the details why. So this first piece just goes to the absolute value of x. That's just a number. This middle piece is going to go to 1 over e, and I will justify that in just a second. And then 1 over n as n goes to infinity goes to 0. So that overall, the result of our ratio test is that for any choice of x, the ratio test computation that we do turns into the absolute value of x times something going to 0. So as n goes to infinity, this is 0. 0 is less than 1 for all choices of x. So what we can say is that no matter what x we pick and plug into this first expression here, the ratio test is going to give us convergence. So this is like r equals infinity. The interval of convergence is from negative infinity to infinity. This converges for all choices of x. So this is what it looks like when your radius is infinite and you get to that result with the ratio test. I wanted to give you just one example of having your power series converge for all possible choices of x, but I picked a little bit of an advanced example. So let me now work out this middle piece so that you can see why it's 1 over e if you haven't figured that out. And then also, just because this was a little bit advanced, I also want to mention another way to do this problem that you might like a little bit better if you're not certain how to tackle this middle component here. So why do I say that n over n plus 1 raised to the n plus 1 goes to 1 over e as n goes to infinity? What I'm going to do for this middle piece is say that this is going to be the limit as n goes to infinity of, let me take this numerator, I'm going to do a trick. This is going to be n plus 1 minus 1. I haven't actually changed anything, but I claim that this is going to be advantageous. So then it's n plus 1 minus 1 divided by n plus 1 to the n plus 1. The reason why I've added and subtracted 1 from the numerator is I'm going to break this fraction into 2 pieces. We'll have n plus 1 over n plus 1, that's just 1, minus 1 over n plus 1. Let me write 1 plus negative 1 over n plus 1. This whole thing raised to the n plus 1. If you don't see the relationship between this and the number e to a certain power, let me take n plus 1 here and just replace it with, say, capital N. So let's take the limit as capital N goes to infinity of 1 plus negative 1 over n to the n, where here capital N is just representing n plus 1. As n goes to infinity, capital N goes to infinity, so that's why I have this prefix here. And then this is literally the definition of e to the negative 1. So it would be e to whatever's in this numerator, that's negative 1. Okay, so that's how I knew that middle piece was 1 over e. But that gives us the result very precisely. What I'm now going to do is compute this limit again. I think I will leave it, let's see, how much will I erase? I'll certainly erase this part. But what we're going to do is use the squeeze theorem instead. Actually, I'm going to erase the whole thing. Okay, let's start all over. But I'm going to use the squeeze theorem to show that this limit is 0 so that we can still get to the radius of convergence without necessarily doing this analysis on this middle term. Okay, let's say that I started trying to evaluate that limit and I got stuck because of the situation that arose where we had different base, different exponent for terms that should have matched. Here's another way to arrive at the limit for that ratio test being 0. What we would like to do is analyze the limit of this expression as n goes to infinity. So it's x to the n plus 1 divided by n plus 1 to the n plus 1 times n to the n divided by x to the n. For any choice of x and any choice of the index n, the absolute value of this expression is greater than or equal to 0. So that's a true statement. What's also true here, maybe I will go ahead and simplify this a bit so that we have absolute value of x times n to the n divided by n plus 1 to the n plus 1. Okay, let me just rewrite this. What's also true is that I have, for any choice of n, positive number being raised to a positive number. These are large numbers. And if I make the denominator smaller, I make this fraction bigger. So what I'm going to do is take n plus 1. I'm going to get rid of the plus 1. That makes this denominator smaller. I'd be raising a smaller number to the same exponent. That makes the fraction bigger. So smaller denominator here, bigger fraction. So we'll have the absolute value of x times n to the n divided by the reduction I'm making. So from n plus 1, I'm going to go down to n to the n plus 1. But now we have a nice cancellation. This is what I couldn't do when I stuck with the expression as it was given to us in the previous computation. Now I can just cancel and say that this is the absolute value of x divided by just one copy of n. We have that the expression we're interested in is between 0 and the absolute value of x divided by n. As n goes to infinity, we still have 0 on the left, and then this is going to go to 0. So this is the key idea here, is that this expression goes to 0 as n goes to infinity. So we have 0 on the left, 0 on the right. By the squeeze theorem, this goes to 0. Because it goes to 0, again, that tells us that any choice of x gives us convergence for our power series. So once again, having a limit here of 0 tells us that the radius of convergence r is infinite.